All right, today we are going to be talking about positive feedback circuits. So in a positive feedback circuit, the output signal, V out, is fed back to the non-inverting input terminal. In a positive feedback configuration, our op-amp circuit behaves slightly differently than what we saw in an open loop configuration. Okay. So in a positive feedback configuration, we should expect to see a decrease in linear range. So previously we saw that our linear range for an op-amp with power supply voltages of plus and minus 10 volts and an open loop gain of 100,000 ranged from negative 100 microvolts to positive 100 microvolts. For a positive feedback configuration, we should see this number get even smaller, meaning that our transition from VCC minus to VCC plus will be an even more vertical line. Okay. We have likely all experienced the effects of a positive feedback system in our lives if we've ever been to any sort of assembly. Okay. So what I mean by that is that if you've ever been to a public event and you have heard feedback come over the loudspeakers, that is actually a positive feedback event. In as much as when a human being talks, the sound is produced by a pressure wave, and that pressure wave is picked up by a microphone and then broadcast over loudspeakers, which amplify the input signal by making an even larger pressure wave. Well, if the microphone picks up the signal from the loudspeakers, it forms a positive feedback loop that drastically gets out of control very quickly. So instead, a small amount of signal gets added back onto itself over and over and over again until we hear that screeching feedback noise that we are all familiar with. Okay. In a circuit, positive feedback can be a good thing. Okay. So a positive feedback amplifier circuit is going to look something like this. We're going to call this first circuit that we're going to deal with a non-inverting Schmidt trigger. And our schematic diagram for this circuit will look something like this. So I'm going to start by drawing my generic op-amp. Here's VCC plus, here's VCC minus, here's my non-inverting input terminal V plus, my inverting input terminal V minus, and my output terminal V out. Okay. I'm going to establish positive feedback by placing a conductive path, usually in the form of a resistor, but not always, could be a capacitor, inductor, or even just a short circuit in some cases, between my output terminal and my non-inverting input terminal. I'm going to call this resistor R2. I'm going to have a resistor R1 that is placed between my my non-inverting input terminal and my input voltage Vin. And then I'm going to apply some reference voltage Vref here at the inverting input terminal. So this is the schematic diagram for a non-inverting Schmidt trigger. We are going to develop relationships for this circuit under a few specific assumptions. Our first assumption is that Rn, the internal resistance of the op amp, is much, much greater than R1 and R2. Our second assumption is that R out, the internal output resistance of the op amp, is much smaller than R1 and R2. So all I'm saying here really is that we're going to pick a value for R1 and R2 somewhere in the kilo ohm range. And our other assumption is that V out, our output voltage, will either be VCC plus or VCC minus, depending on some criterion we have yet to define. The reason we're making this assumption is because we have a positive feedback circuit. And since a portion of the output is getting fed back into the non-inverting input, we should observe, due to our decreased linear range, that our output will saturate at our power supply voltages very, very easily. Okay, more easily than in an open loop configuration. So here are our assumptions. Now I'm going to draw the practical op amp model representation of our circuit. As usual, I will start with the practical op amp model for the op amp itself, and then I will append that depiction with our connections that are specific to the circuit we're analyzing. So here's my input resistance Rn, my non-inverting input terminal V plus, my inverting input terminal V minus, and my differential voltage Vd. So this is what we have on the input side of our practical op amp model. Here I have my differential voltage amplifier, AVOL VD, connected in series with my output resistance R out. And I have my ground rail for the circuit. So this is my practical op amp model. Now let's make our connections. So between the inverting input terminal and ground, we have some voltage V reference. Between the non-inverting input terminal and ground, we have our resistor R1 in series with our input voltage. and connecting our our non-inverting input terminal to the output terminal, we have some feedback resistance, R2. So, and our output voltage V out is measured from our output terminal with respect to ground. So this is what our practical op-amp model circuit looks like. And what we are going to do here is we are going to apply Kirchhoff's current law at our non-inverting input terminal. So I'm going to be adding this current plus this current plus this current together, and we will see what comes from this analysis. So applying KCL at the non-inverting input terminal, we will have V plus our non-inverting input voltage minus Vn over R1. We will have V plus minus V out over R2. And we will also have V plus minus V ref over Rn. We're going to set this equal to 0. So if we bring our assumptions into play, specifically that first assumption that the resistor R1 and R2 is much, much smaller than our input resistance, what that means is that this term here effectively goes to 0 because it will be so much smaller than the other two terms for our current. There is a convenient outcome that we can conclude from that, okay? So if the current that is flowing through our input resistance is essentially 0, our differential voltage VD is going to be very small, which means V minus, which is the same as V ref, is approximately equal to V plus. So let me write that down, okay? So if R1 and R2 are much smaller than Rn, then VD is approximately 0 volts, and thus V plus is approximately equal to V minus, which is equal to V ref. Under this constraint, our equation becomes V ref minus Vn over R1 plus Vref minus V out over R2 is equal to 0. And now we're just going to do some simple algebraic manipulation of this expression. So that's going to look like Vref over R1 minus Vn over R1 plus Vref over R2 minus V out over R2 is equal to 0, or Vref times 1 over R1 plus 1 over R2 is equal to Vn over R1 plus V out over R2. Now, as a brief aside here, quantity 1 over R1 plus 1 over R2 is the reciprocal of R1 in parallel with R2, right? Because R1 in parallel with R2 should look like 1 over R1 plus 1 over R2. So we can express that as R1 plus R2 over R1 times R2. Well, when we divide both sides by that fractional representation, it's the same as multiplying by the reciprocal, meaning we are going to find, let me go to the next page here, that we will have an expression Vref is equal to R2 over R1 plus R2 times Vn plus R1 over R1 plus R2 times V out. And this is our characteristic equation that tells us how our non-inverting Schmidt trigger behaves. We're going to use this equation to determine what are called our upper and lower trigger limits. To get a better understanding of what this concept of upper and lower trigger limits means, we are going to run a simulation. I just have to find the right folder. So this is a simulation that I developed for the spring of 2022 when I was teaching this material. And it goes into effectively why a Schmidt trigger behaves the way that it does, and why we might go about using one. I'm going to just make a couple of simple alterations here just so that we get something slightly new. So let's call this a 4-volt source, and let's make R1 in this case a 2 kilo ohm resistor. And for right now, I'm just going to apply my sinusoidal input voltage. And we're going to run my simulation. Let's get rid of this. And I want to look at my input signal, which is a simple sinusoid ranging from positive 10 volts to negative 10 volts. And then my output signal. I'm going to play with the boundaries here very briefly, just for the sake of making it more easy to observe what's happening. So effectively, we get an output signal that is very similar to what we saw for our comparator, right? When we had our comparator, when we put a sinusoidal signal in, we got a square wave out. And we saw that whenever Vn was greater than V reference, our output went high. And whenever Vn was less than our reference voltage, our output went low. Our non-inverting Schmidt trigger has a very similar output response, except that it includes what I'm going to call latching, okay? So effectively, there are two different thresholds that the Schmidt trigger uses instead of a single reference voltage. One of which is called the upper trigger limit, and the other of which is called the lower trigger limit. The upper trigger limit is the input voltage that causes the output to go to the to saturate to VCC plus, and the lower trigger limit is the input voltage that causes the output to saturate to VCC minus. So if we look at our graph right here, hopefully you guys can see my cursor kind of swirling about this point. We can see that a voltage of somewhere close to 7 volts is our upper trigger limit, because our output signal goes from VCC minus to VCC plus whenever our input signal hits this value. And then our output stays high at VCC plus until our input signal gets more negative or lower than our lower trigger limit, where our output switches from VCC plus down to VCC minus. So now I'm going to swap back here, and we are going to develop mathematical relationships for these things. First, upper trigger limit. We're going to define it to be the value of Vn causes V out to change from VCC minus to VCC plus. So let's throw some numbers in here, right? If we look back at the schematic diagram that I have, we have a VCC plus of positive 10 volts, a VCC minus of negative 10 volts. So let's write those down. we had a reference voltage of 4 volts. We have an R1 value of 2 kiloohms. And we have an R2 value of 10 kiloohms. So if we substitute numbers into the equation that I have boxed in red, what we're going to have is V reference, or 4 volts, is equal to R2, which is 10 kiloohms, over R1 plus R2, so that's 2 kiloohms plus 10 kiloohms, times our input voltage Vin, plus R1, which is 2 kiloohms, over R1 plus R2, 2 kiloohms plus 10 kiloohms, multiplied by V out. Since we're trying to solve for the upper trigger limit voltage, V in, V out has to be VCC minus, or negative 10 volts. Because the whole point is for us to determine what causes the output to change from VCC minus and swing up to VCC plus. So we can do a little bit of algebraic manipulation here. So we're going to have 4 volts is equal to 10 over 12 times Vn minus 2 over 12, excuse me, plus 2 over 12 times negative 10 volts. So this is going to look like 4 volts plus 20 over 12 volts is equal to 10/12 times Vn. And therefore, Vn, our upper trigger limit voltage, is 12/10 times 4 volts plus 20 over 12 volts. And let's throw this into our calculator and see what we get. So I get 34 over 5, which, if I'm not mistaken, is 6.8 volts. So this is our upper trigger limit, UTL. Let's look back at our graph here. A voltage of 6.8 volts makes sense? According to the graph, the answer is yes. We can verify this a little better by simply adding a trace that is volts. And we see that that is indeed the intersection of our output curve and our input curve. So we have determined our upper trigger limit successfully. Okay. Now, let's work on our lower trigger limit. So we are going to define our lower trigger limit to be the value of Vn that causes the output voltage V out change from VCC plus to VCC minus. So for our particular op amp that we modeled, we are going to have effectively the exact same equation that we had before. Our reference voltage, 4 volts, is equal to R2 over R1 plus R2. So that's going to look like 10 kilo ohms over 12 kilo ohms times Vn plus R1 over R1 plus R2, so 2 kilo ohms over 12 kilo ohms, times V out, where in this case, V out is at VCC plus, and we're trying to figure out what pushes it to VCC minus. So this will be positive 10 volts. And we're again going to just simply manipulate this algebraically. So 4 volts minus 2/12 times positive 10 volts is equal to 10/12 times Vn. And so Vn is going to be 12 over 10 times 4 volts minus 20 over 12 volts. Which comes out to be 14/5 of a volt, or 2.8 volts. This is our lower trigger limit. Let's look and see if that agrees with our simulation. So somewhere between 2 and 4 volts. So we've got agreement there. We'll just put in this mathematical expression. And that is indeed where we see our lower trigger limit is. Right? So our model and the assumptions that we have made are actually doing a very, very good job of predicting where our upper and lower trigger limits will be for an op amp circuit. All right, so before we move along to inverting Schmidt triggers, I want to show you guys something that I believe to be pretty interesting. And what we're going to do is we're going to talk about why you would use a Schmidt trigger versus a comparator. Okay. So if I run a simulation here, and I have a noisy input signal, so that's what this Vn plus N means, where I've simply added some amount of white noise on top of a sinusoidal waveform. My input signal will look something like this. And for a comparator, my output signal will look something like this. When I have a lot of noise around my reference voltage, what will happen is the comparator will swing back and forth wildly from VCC plus to VCC minus. Okay. So we're not getting a clean transition from a digital high state to a digital low state in our comparison. If I instead, let me delete these traces, have that same input signal, actually let me in plus N. If I apply that exact same input signal to my Schmidt trigger circuit and look at my output, I do have that nice clean transition. And the reason why I have the nice clean transition from VCC or plus down to VCC minus is because of that latching that I discussed earlier. So effectively, the output stays high until the lower trigger limit is reached, and then the output stays low until the upper trigger limit is reached. We can play around with our results here to make those trigger limits near each other, or we can use widely spaced trigger limits to make special comparisons. We can actually improve on our one bit digital to analog converter that we designed in class on Wednesday, and that's actually one of the design problems I've asked you to do for the op-amp design project assignment. All right, so now let's look at the inverting comparator. Inverting Schmidt trigger. So our inverting Schmidt trigger circuit is going to look extraordinarily similar to our non-inverting Schmidt trigger circuit. So we have our op-amp. Here's our positive supply voltage, VCC plus, our negative supply voltage, VCC minus, our output pin V out, our non-inverting input terminal V plus, our inverting input terminal V minus, and we are going to apply positive feedback. Just as we did before. So this is resistor R2. The change that we're going to make is we're still going to have this resistor R1 applied between the inverting input terminal, but instead of having our input signal applied at the left leg of R1, we're going to apply our reference voltage here. And we're going to apply our input signal directly to the inverting input terminal. So this is literally the exact same circuit as we had before, except that we have swapped these two voltages. So I would argue that we do not need to do a rigorous analysis of that circuit. We can simply take the results of our non-inverting Schmidt trigger and swap V in and V reference. In doing so, we get the relationship Vn is equal to R2 over R1 plus R2 times V reference plus R1 over R1 plus R2 times V out. This is the equation that lets us determine our upper and lower trigger limits for our inverting Schmidt trigger, where the upper and lower trigger limits are defined in the exact same way. The upper trigger limit is the input voltage that causes V out to change from VCC minus to VCC plus, and the lower trigger limit is the input voltage that causes V out to change from VCC plus to VCC minus. Graphically, the output is going to look the exact opposite as what we saw for our non-inverting Schmidt trigger, just like the response of a inverting comparator was exactly opposite to that of a non-inverting comparator. All right, the last circuit that I want to talk to you guys about for today is the op-amp multi-vibrator circuit. This is a very interesting circuit in as much as it does not have an actual input signal to process. So in an astable multi-vibrator circuit, we're going to have our op-amp. Please note that in this particular case, I have decided to put the inverting input terminal on top. I have VCC plus up here, VCC minus here. Here's V minus. Here's V plus. Here is V out. So we have our basic op-amp. Now I'm going to apply my positive feedback. I'm going to draw it slightly differently than I have done previously, but it is still positive feedback because there is a connection between the output node and the non-inverting input node. Let's call this resistor R1. And then we're going to have a resistor here. R2. We are also going to be employing negative feedback in as much as there is a feedback connection between our output node V out and our inverting input terminal. We're going to call this resistor R. So this circuit employs both positive feedback and negative feedback, but the effects of positive feedback are going to dominate the response. So we should see that the output voltage swings from VCC plus to VCC minus. And we're also going to have one other interesting feature here, a capacitor. So this guy is not a purely resistive circuit. Let's call this capacitor C. And I'm going to call this voltage at this node, VC, the voltage drop across the capacitor with respect to ground. And I'm going to call the voltage at this node, which is effectively the voltage at the non-inverting input terminal, the reference voltage for the circuit. So we're not going to get into a highly detailed analysis of how this circuit works because it is rather complicated, but we can describe what's happening qualitatively to understand what's going on. So our first assumption here, our first part of our description will be, we are going to assume that our capacitor VC, our capacitor voltage VC is 0 volts, which means we're assuming our capacitor is not yet charged in any way, shape, or form. And we're going to assume that our output voltage V out begins at VCC plus. So our output voltage is saturated at VCC plus. So in this particular case, with VC equal to 0 and V out equal to VCC plus, what we are going to see is that current will flow through our resistor R and will begin charging our capacitor at a rate determined by the time constant R times C. An additional consequence of V out starting at positive 10 volts is that our reference voltage, V ref, in this case, will be a positive voltage. I'm going to write that down. Current flowing through R causes VC to begin to increase charging the capacitor at a rate determined by R times C. And I'm going to supplement this description with a graphical representation of our various signals here. Okay, so let's plot the out as a function of time. Let's plot VC as a function of time. Actually, sorry. These should just be time. This should be V out here, C here. And this will be V ref here. So we're starting from a place where our output voltage is high. Our reference voltage is positive, and our capacitor is beginning to charge. As soon as VC reaches V ref, which is V out times R2 over R1 plus R2, because we have a simple voltage divider circuit here. Our output voltage V out will swing to VCC minus. So our next stage, we are going to see V out swings to VCC minus, which in turn causes V ref to swing to a negative value. And now our capacitor will start to discharge until it reaches the negative value of V ref, and then the cycle starts again. So effectively what we should observe something like this. So what we have made here is an oscillator circuit or a clock circuit, right? We don't have any true input signal whatsoever, but we see that our output switches back and forth between VCC plus and VCC minus at regularly defined intervals that are determined by the rate at which the capacitor charges and discharges. Our period, so let me write this fourth stage here down. The capacitor now discharges until VC reaches Vref again. All right, so the period of oscillation T is given by twice RC times the natural logarithm of 1 plus beta over 1 minus beta, where beta is determined to be R2 over R1 plus R2. So we can design an oscillator circuit where we can get large changes in the period of the oscillation, right? So let's define that real quick. Here is our period, capital T. If we change either R or C, and we can get small changes in the period if we change the values of R1 or R2. And I believe I thought I had an astable multivibrator circuit saved. Let's see if I have one here. Does not look like I do, so we'll draw one real quick. So I'm going to start with universal op amp 2. Let's just drop this here. I'm going to give myself a stub of wire connection here, a stub of wire connection here, a stub of wire connection here. And I'm going to set up my power supply voltages right now over here on the left-hand side of the circuit and go ahead and put those in so that I can wrap my feedback around cleanly. So let's make this positive 10 volts, 10 volts here. Let's call our top voltage source VCC plus, our bottom voltage source VCC minus. All right, so here's the out over here. So let's put some resistors in. So here's R1. Here's R2. Now we're going to need to do our positive feedback path. So here is our resistor R. We're also going to have our capacitor C, which I will just tuck down here. And let's label some things here. So let's call this BC. Let's call this VREF. And let's give ourselves some values. So let's do 1 millifarad, 10 kiloohms, 1 kiloohm, and 2 kiloohms. And I'm also going to have to do something special here. I'm going to have to give my capacitor some initial amount of stored energy. Okay. In our loose derivation, we did not do this, but we are going to need to do it for our simulation here because we're dealing with an idealized circuit. So effectively, we need to give the circuit a very small push to get it to start oscillating, at which point it will continue to oscillate. So I'm going to do that by saying that the voltage at node VC is equal to 0.001. Or effectively, I'm saying that there is a 1 millivolt voltage drop across our capacitor, and this should be enough for us to cause the output to start oscillating. Let's do a transient analysis, and let's look at it for 1 second, and we'll likely wind up having to adjust this in a little bit, okay? Yeah, let's look at it for 100 seconds and see what happens. Oh, one problem that I just noticed is I didn't attach VCC plus, there's going to be VCC minus to an actual voltage. So that's likely causing a few errors here. All right, so 100 seconds isn't quite enough to get it really swinging. So let's look at it for 1,000 seconds. There we go. Okay. So because we have a very small amount of energy stored in the capacitor, it takes some time for things to swing up. But once it gets oscillating, it continues to oscillate at that fixed interval. If we were to change this instead of 1 millivolt to, let's call it 100 millivolts, we should observe that it starts swinging or oscillating much more quickly. Exactly. Yep. In a real or practical astable multi-vibrator circuit, we wouldn't really need to do this because there's going to be effectively enough thermal noise to start the process. But because we're dealing with an idealized circuit, we have to give it a little push. Let's change this to 100 again, now that we've got a value that causes it to start oscillating pretty well. So we can see that it has a period of about 27 seconds. If we were to change our resistor value R, we see that the period changes, right? When we reduce R, the period changes, which is exactly what our mathematical expression tells us. Similarly, if we make C larger, so instead of 1 millifarad, let's do 25 millifarads. now we're having trouble charging the capacitor in that amount of time again. Let's scroll this out. Actually, let's just make this easier and just do this 2.5. We make the period longer, okay? And changing R1 and R2 will also allow us to change the period of oscillations. So this is a simple clock circuit that's used in a lot of electronics applications because it requires no input signal to get it going. You can simply design it to have a specific oscillation frequency and then go from there. All right, so that's enough out of me for today. When we meet on Monday, we will start talking about negative feedback amplifiers. And I believe we will be wrapping up our discussion of op-amp circuits by the end of next week. So thank you all for your time, and I will see you on Monday.